Hi, Year 12s. So we're up to subtopic 2.1, rates of reaction. And the first thing we're going to be looking at is the interpretation of graphs, specifically graphs that show the quantity of a substance, a reactant, or a product, and showing that over time. Now, these two graphs here, they are assuming that we start with all reactant and no product. The left-hand side, we have our reactants, which have some sort of quantity. On the right-hand side, we see our products, which start at 0. At the very start of the reaction, we have the greatest amount of our reactant. Because we have so much of it, we're going to have the most number of collisions occurring between those, which will lead to a faster reaction into products. And we actually see that as the quantity is decreasing, we can notice that the slope itself of that line is decreasing as well. At the very top, the slope is the greatest. That's showing that at that moment, at the start, the reaction is the fastest. As we get move forward in time, the slope is decreasing, which shows that the reaction rate is decreasing as well. So just to summarize, the slope of the graph of quantity of our substance over time, the slope of that is the reaction rate. So how quickly we are losing that reactant and it becoming products. Similarly, over here, you'll see our reaction rate for our products forming is the greatest. So the slope here is the greatest. And then as we move along, we see the slope decreasing. This is due to pretty much the exact same reason why we have our reactants becoming products the fastest. Obviously, our product increase is going to be the fastest at the start. Now, both of these, what you'll notice is that because it's decreasing, it's going to eventually flatten out over time. So after a certain amount of time, the reaction, or the slope of this line will be flat. That represents no net reaction occurring anymore. Now, it's very important. When I say no net reaction, what that means is the molecules themselves are not or haven't stopped reacting. We're still getting reactants becoming products, but we're also getting products becoming reactants. The backwards reaction, those two reactions are occurring at the exact same rate. Now, if that's occurring, the rate forward and the rate backward are the same, we don't see any changes in our quantities, even if we would be able to see changes if we could track individual molecules. So we are seeing molecules go forward and become products, we're seeing them go back and become reactants. That rate is the same. So moving on, these quantities that I mentioned here, those can be measured in a number of ways. So a common way would be to measure the mass of a reaction mixture. This first example here, we see calcium carbonate reacting with hydrochloric acid. It becomes calcium chloride, water, and CO2, which is gas. Now, if our reaction container is open at the top, that gas will bubble away and our reaction mixture will become lighter. So as our reaction mixture becomes lighter, we know that the reaction has moved forward and has made our gaseous substance. Now, in this particular case, the backward reaction is not really relevant because that carbon dioxide gas has left the reaction container, so it's not available to make the backward reaction occur. So in this particular case, we would keep dissolving as long as we have enough hydrochloric acid, we would keep dissolving our calcium carbonate until there's none left. So our reaction quantity up here would start at a full greatest amount and it would decrease over time till, assuming there's enough hydrochloric acid, our calcium carbonate went to 0. As I said, we could measure that using the mass of our reaction mixture. So the mass would be the maximum at the start and that would decrease over time. Another way would be to look at another quantity that changes as the reaction proceeds. If we react sodium metal with water, we get the formation of sodium hydroxide as well as H2 gas. Now, similarly, as this reaction occurs, the H2 gas will leave, meaning our reaction is mostly just going to go forwards. We're not going to get any backwards because the H2 is no longer there. Regardless, we could measure the mass with our decreasing H2, but we could also have a look at sodium hydroxide and measure the pH. because sodium hydroxide is going to change the pH of our reaction. It's going to make the reaction mixture more basic. We could measure the pH over time, and then we could see how quickly our reaction's occurring. You'd expect that the pH would change most quickly, or at least the concentration of sodium hydroxide would increase most quickly at the very start of our reaction. Now, moving on, we're going to be looking a little bit more deeply into the different factors that contribute to our reaction rate. Now, this sort of stuff has been looked at, very briefly, probably in year 10, maybe even last year, but we'll go into it again. So, the first thing you need to remember is that for a reaction to occur, chemicals or molecules must collide with each other. They must come in contact successfully. Now, successfully can mean a few things. The first one that I'm looking at here is that they must come together in the correct orientation. Now, if we look at this example here where we're taking our N2 molecule and our O2 molecule, and we want to react them into two NO molecules, it seems hopefully obvious that for this N and this O to combine, they're going to have to come into contact directly. Similarly, at the exact same time, we're going to have this nitrogen and this oxygen come into contact so that both of these NO molecules can be created. So if they were to come into contact, so this molecule here and this molecule here come into contact side on, just as I've illustrated it, that reaction may be successful. However, if the molecules were to collide end on, so for example, like we've drawn it here, these two nitrogen and oxygens come together, but the other two do not, that would not lead to a successful reaction. You'd only have one of them interacting with one nitrogen and one oxygen, So that this first collision, if that was to happen, that would be successful. The second one would not. Therefore, we don't only have to have them colliding more often. So if they hit together more often for a reaction to happen faster, they have to hit together more often successfully. Now, the second bit that makes them successful is this bit here. If the molecules come together, just because they have come together in the correct orientation doesn't mean that they will actually undergo a reaction. This is because many reactions have what's called an activation energy or an activation barrier. This is because when these two molecules, for example, come together, these bonds here will need to break. There needs to be some sort of, it takes a little bit of energy for that to break before the new bonds can form. And that energy has to come from somewhere. Usually it's going to come from the internal energy of the molecules themselves when they're coming together. So molecules come together with sufficient energy, they will react. Molecules coming together with sufficient energy but in the wrong orientation will not react. Now, here are the following factors that can impact some of those. The first being concentration. Now, the concentration, hopefully you know, is essentially the density of our molecules within a certain volume. So the greater the concentration, we have more molecules in a certain space, which means they're going to be closer together, they're going to collide with each other more often. And if they collide with each other more often, you're going to have some percentage of those being in successful orientations with enough energy, so you're going to end up with an increased frequency of successful collisions as well. So the reaction rate will go up with increasing concentration. That is part of the reason why. Well, actually, that's the reason why you see the greatest slope being at the start of our reaction. Our reactants have the highest concentration, so they're going to react most quickly. Now, the second thing that I'm going to consider is temperature. Now, temperature has an effect in a couple of ways. The first being an increase in temperature will give our molecules a greater amount of energy, which will allow them to overcome their activation energy barrier. So every time your molecules are colliding, if they're hotter, they have more energy, they're more likely to overcome that barrier and cause a reaction to occur. Additionally, so as I've written just up here, if you have hotter molecules, they're going to be moving around more quickly, which means they're going to collide more frequently. as such, the greater frequency of collisions means that they are going to hit each other in the right way more often as well, causing reaction to occur. Now, the third one here, we have pressure. Now, pressure is specifically referring to gases. So when we have gases, the greater the pressure, the more molecules there are in a certain area. So it's analogous to concentration in this case. So if we have an increased pressure, we have more molecules. They're bumping into each other more often. They're going to hit each other in the correct orientation more often. And so we're going to end up with more frequent collisions, which ends up with a greater reaction rate. The reaction happening more often. Now, when we look at surface area, this is again, the previous one, pressure, is more for gases. Surface area is for solids. If you have a solid chunk and is reacting with some stuff around it, if it's a circle, like for example a sphere, there's a whole bunch of our solid in the center that is not coming into contact with our other reactant. If instead we break that up and powder it up, it's going to have a lot more contact with our reactants, our other reactants, so that will increase the rate. Now, the last one I'm covering here are catalysts. Now, you can find a number of different catalysts. So if we go up here, you can actually see they talk about inorganic and biological catalysts. So inorganic being some sort of chemical, biological being some sort of protein or enzyme that does the catalysis. Regardless, the process of catalysis is the same. The catalyst is some sort of substance and allows the reactants some other way to react that has a smaller activation barrier. So we're going to look at activation barriers in a minute. Regardless, we have our activation barrier, say that's this high. Our catalyst will reduce that activation barrier so that there will be more successful collisions occurring. So a greater proportion of collisions will be successful because the activation energy barrier is smaller. Now, there's a few ways that can actually happen. I'll just give you a couple. A catalyst can make it so that the process that has to happen when a reaction occurs doesn't require as much energy. So let's say if we go back up to this example here, this bond has to break. If our catalyst grabs onto this and starts pulling it apart, it will help this bond break, which will lead to less energy being required. What it can also do is it could, for example, hold molecules in the correct orientation, so that instead of molecules coming along and bumping into each other any which way, they are instead going to come into contact with one molecule that's being held in the proper orientation, so that a greater proportion of the collisions that occur are successful again. So the last bit here, we're looking at energy profile diagrams. So these diagrams show the energy of our molecules as the reaction proceeds. So we have energy on the left, and the bottom here says reaction pathway. Now this one at the bottom here, there are a lot of different ways that can, or you can write that bottom axis, that label. It can be reaction pathway, reaction coordinate, reaction progress. Either way, as our reaction is moving on, we can see what the energy of our substances do. Now, on the left, you're always going to have your reactants, and on the products, on the right, you're always going to have your products. Now, even though reactions can be moved, can be swapped over, so we have our reactants and products switching, as we'll see in our next subtopic, it will still have the reactants on the left of this diagram, the products on the right. You'll just have the entire thing flipped around. But again, you'll see this occurring. Now, there's a few spots to fill in for this one. So as we move along, this diagram on the left here, the top one, so there is one below, but we're talking about the top one. It is endothermic. Now we can see that because as our reaction proceeds, we go over our transition state and we end up with our products having a greater energy or greater enthalpy than our reactants. Now, enthalpy is just another word for internal energy. So that energy has been stored in our molecules. And if our reactants are here and our products are here, the enthalpy or the energy has gone up. And if that happens, our reaction is endothermic. Energy has been taken in to the molecules, and normally that comes from the surroundings. So we end up with our surroundings feeling colder because the energy has been sucked away into the bonds of the molecules themselves. Now, when it comes to our reaction rate, you will see here that if we have our reactants, they've got quite a large barrier to get over to get to our products. So we're going to see relatively few, unless the temperature is high, relatively few of our reactants have enough energy to overcome this barrier, which is going to mean that our reactants aren't going to, not a heap of them, not a lot of them are going to be becoming products. Now, temperature, when we have a substance at a temperature, there's actually not a simple way of thinking about the movement of those molecules. It's not that at a certain temperature everything's moving at a certain speed the same. At a certain temperature you're going to have a range of movements, a range of energy that those molecules will have. Some really low energy, some really high, but it'll be centered around a certain amount. The important point of that is that there will be some molecules at any temperature with more energy, and so you will get some that have enough even at a lower temperature. Now, this bit here I just spoke about, that will become a bit more obvious when we talk about equilibrium as well. So this second one, it looks very similar to the first one, although it is inverted, so it's switched left and right. Instead of having our products having our high energy, we have our reactants. Instead of our reactants having a lower energy, it's our products. And this one here is an exothermic, a diagram representing an exothermic reaction. Now, like I said just here before I move on to that next bit, if we do increase our reaction temperature, we have more molecules with enough energy to overcome that barrier, and so our reaction rate will increase. Additionally, this barrier is the thing that can be reduced, something like this, with a catalyst. That will also mean that more molecules have enough energy to overcome this smaller barrier than they would have had this larger barrier. Now, moving on to this last one, the axes are the same, energy and reaction pathway here. The difference is that our reactants going onto our products will end up with a decrease in enthalpy. So our products have less energy than our reactants inside their bonds. That energy that they've lost has to go somewhere, and it's going to go into the surroundings, which is going to make the surroundings feel hot. So even though we've lost energy, decreased, the surroundings feel hotter because we're not looking at the energy of the molecules themselves, we're looking at the energy of the surrounding substance. For example, water, if it's an aqueous reaction, the water is absorbing the energy that's being released by the molecules that are doing the reaction themselves. Now, one thing you might also notice is that if we're looking at reactants, the energy gap that they have to overcome, this EA, is actually quite small. So that means they're going to have a larger proportion of our reactant molecules at any given temperature having enough energy to overcome, especially when compared to our products that might be trying to come back and have a much bigger gap barrier to overcome. Now, hopefully this is a good introduction. I hope I haven't missed too much. We'll be covering more of this sort of concept in the next subtopic as well, especially because it covers equilibrium, which tells us that we can have our products coming back to form our reactants, as well as our reactants going forwards to become our products. Good luck.